So today I'm going to be talking about XenStore security, and to talk about to explain why we need to talk about XenStore security, I'll be starting from this example where we're a hosting provider, we're using Xen, and we're providing virtual machines for two customers. We have DOM1 and DOM2, two different customers. And to me, one of the guarantees that we want to make in this situation is we want to try to assure as much isolation as possible between DOM1 and DOM2. We don't want to allow communication between these two domains unless we specifically decide to allow that communication. So one tool that we have as Xen administrators is the Flask module with the Xen security modules, which is a mouthful, so I'll just call that XSM for the rest of this talk. So using XSM, we can write a mandatory access control policy that states that DOM1 and DOM2 cannot communicate at all. No shared pages, event channels, that sort of thing. There's a problem with XenStore, though, and that if DOM1 and DOM2 can read and write the same shared nodes, it allows them to communicate. And this communication is not something that we have good control over with XSM. It's not fine-grained enough. So really the problem is that XenStore allows information to flow between domains, and that flow is not under the control of the XSM policy. The only real knob we would have to turn with XSM would be to completely disallow communication between the domain and XenStore. I'm going to skip this slide because Jonathan had an older version of my deck. All right, so where we're going to start with is the access control that's built into XenStore and why that's not enough to address this situation. So XenStore's access control is what we call discretionary. And that means that nodes in XenStore are owned by a particular domain. And a domain that owns a node has basically permission to do anything it wants with it in terms of its permissions. So domains can grant permissions to other domains. And we have no control over this as the administrator. Turns out it's very easy to use XenStore's access control to communicate information from one domain to another. So here we see DOM1 can write presumably secret data to a node that it has full control over, and then give that access to that node away to domain 2. And it's very simple for domain 2 to read that back out with XenStore read. So next we'll be looking at how adding mandatory access control to XenStore can address this situation. So when we have mandatory access control in XenStore, we write in the security policy all the accesses that are allowed. So we essentially start from nothing. And we say everything is denied except for the things that I say you can do. And once that's in place, domains can't change that unless you, as the administrator, specifically give them the power to do that. And so in this case, because DOM1 doesn't have control over the access to its nodes, we were closing up that information flow there. So how this works in the context of XenStore, this is mandatory access control 101 really quick in 2 slides here, is we take all the objects in the system that we care about. In our case, it's Xen domains and it's XenStore nodes. And we assign them a security label. And for our purposes, we can think of that as a string. It's a free-form string. We can use any sort of conventions we like. And so here are some example XenStore nodes where we've given them some labels. I've prefixed them with XS to indicate that they're XenStore nodes. We can also see that they have some information about which domain they belong to, so DOM1 versus DOM2, and then also information about where they are in the XenStore hierarchy, so the fact that these are data nodes. And in my example, domain ID, the number 1, happens to be DOM1, but that's not anything that needs to be the case. DOM IDs are dynamic, obviously, so this could be 3, but it may still be called DOM1. That's the domain's name. So once we've labeled the objects in the system, then what we do is we write a security policy where, again, starting from everything is denied, we write rules that allow accesses to occur based on who's doing the request, what object they're requesting access to, and what type of request they're doing, whether it's a read, write, etc. So some examples here. So in this first one, DOM1T is the security label for a domain, so domain 1. On the right in blue, we have XS DOM1 data T, which is a XenStore node. That's DOM1's data, the label for DOM1's data nodes. And what we're allowing the domain to do is read, write, create, and delete those nodes. And so this type on the right could correspond to a single node, it could correspond to a whole set of them. But as long as the label of the node is that, those accesses are going to be allowed. Second example here is of the same form, but it's allowing DOM2 access to its data nodes. So DOM2 can access nodes that are labeled with DOM2. Well, so each domain has access to the nodes that it owns, but what we explicitly don't see in here is anything that allows any sort of cross-domain access. And unless we write those rules, that access just can't occur because we have not given the domains the ability to change the permissions of their nodes. So this is how we close that information flow between DOM1 and DOM2, by making more fine-grained security decisions, by actually looking in XenStore operations. So next I'll be talking about Galois' implementation of mandatory access control for XenStore. So we started with XenStore from Mirage, Mirage OS, and it's an excellent XenStore implementation. It's under very active development. The development is so active that we're actually a little bit behind in our patches. And we also think that a unikernel type architecture like Mirage is a good fit for XenStore. XenStore is something that's pretty easy to pull out. It doesn't need a lot of OS support. So it's a prime candidate for running in its own domain in this way. One goal that we had with this work is that we wanted XenStore's security policy to stay inside XenStore. We didn't want to float it up into the hypervisor. A lot of the sort of user space object managers that you find in SELinux, they put all the security policy in the kernel policy. So you see a lot of stuff for like X11 in the SELinux reference policy. We wanted this to be able to work in a situation where you might not have control over the hypervisor's security policy. So perhaps that's set by your hardware vendor, for example. We still want to be able to write interesting XenStore policy. The problem there is that when we would reference domains in XenStore, those labels come from the XSM policy. So in a sense, we have some nesting of security servers going on here, where there's an outer XSM policy with an inner XenStore policy. And so we need a way to be able to import security IDs from the parent. So the way we do that is we use what's called a context database, which is a very simple file that just maps security IDs from the parent to security IDs in the child. And that mapping can be one-to-one, can be many-to-one, or one-to-many, however you like. And that covers a lot of bases with how your hypervisor policy is written. In all of our examples, it's one-to-one, so I don't actually show any examples of that, but that flexibility is there if it's needed. So going down a level in the design, we've taken what is the sort of typical approach when adding MAC to a system, and that we've made it modular. So we've added a security module interface to XenStore. And this module, you can think of it as a structure with a bunch of function pointers in it. That's how it works in Linux with LSM and Xen with XSM, where there's a function for every sort of access you would do, like read, write, create. And those return allow or deny, basically. And so by default, you're using a set of dummy hooks that just allow everything. And so when you're using the dummy hooks, you just have the status quo where you use Xen's built-in access control. It's discretionary access control. So when we enable Flask or MAC in XenStore, we switch those hooks over to hooks from our XenStore+MAC module. And so these use the C library libsepol, which is a standard SELinux library, to load the binary policy and do access checks against it. And we're also able to use the standard policy compiler to compile our policy to this binary. Interesting data point, we use a Linux-style policy, not a Xen-style policy, because we don't need the special sauce that's in the Xen version of the binary policy. And along with that, we have the context database that I mentioned for nesting, and we also have a path database that's used for labeling nodes. And this is similar to an SELinux file context file, if you're familiar with SELinux. So finally, what I think is really the interesting part here is what is some of the cool policy that we can write once we have this system in place. So the first big problem that you have to tackle when you're adding MAC to XenStore is how you're going to label nodes. This turns out to be probably the most complicated part of how this all works. So here's an example of a very abbreviated XenStore tree and how we might want to label it. We can see that like the root, a couple directories have the same label, and then we start saying, okay, now we're in domains, and now we have nodes that are specific to a domain. So we have some DOM1 and some DOM2 nodes. I'm actually going to jump around to this and then come back to that. My apologies. So the default rule with labeling is that when we create a node, we inherit the label from its parent. Very simple. when we want to override that, we take the path that we want to override the behavior for, and we add an entry to the path database. And we use that to inform a type transition in the policy that actually computes the label. So the core thing here is that there's a two-step process for computing the label of a node. And we'll see why that's important here in a minute. So this is what the path database file looks like. I'm going to start with this local domain here. And so what we're saying is that if we're creating the node /local/domain, that path has a type of access local domain path T. Now, the interesting thing here is that this label is not for that node. It's a label for the sort of abstract idea of this path. So the path has a label. And then what we do is we write this first type transition here, where we have the parent node in blue and the path type that we just saw in the path database in green. So what this is saying is that if I'm creating an excess local domain path T, and I'm creating it with a parent of excess root T, then the computed label is in red here, excess local domain T. So this means that the reason we have this level of indirection is that this local domain path T might result in a different computed label if it were somewhere else in the tree. So we have control over labeling based on where the node is actually occurring in the layout of XenStore. So I'm going to skip to the third line here where we look at local domain /star/data. So this is a similar rule to the first one, except we have a wildcard in here. And these wildcards aren't globs, they're not regular expressions. They're literally like a single token that says one path element can occur here. So it's a very simple form of wildcarding. Obviously, the intent is that there's a DOM ID in there. So if this is local domain 1/data, local domain 1 is going to have some type. And it turns out that that type is in line 2 here in blue, excess DOM1 control T. So now we've matched that path, and the label of the path is domain data path T. So then the computed label in red on the second line is excess DOM1 data T. So here we've used that wildcarding to inform the policy about how to compute the label for that node. And finally, we'll look at the middle line here, which doesn't have a label. So this is a DOM rule for local domain /star. And this is where the nesting of security servers actually occurs. So when XenStore sees this rule, and we create, say, local domain 1, we use this third type transition here that actually looks up 1 as a DOM ID, and it goes and asks Xen and says, Xen, what's the security ID for domain 1? And Xen says, well, it's DOM1T. And then we map that to our notion of what DOM1T means using the context database, probably still DOM1T in my example here. And then we look at the parent node again, which is local domain T, and then we can compute in red, again on the last line, the final label of the newly created node. A little bit of complexity here, but the main thing to take away is that we use this level of indirection so that we can sort of not have to worry about the dynamic nature of DOM IDs. We can look those up and then use them to do the second step where now we know the security context of the domain. We can use that to compute labels for that domain. So another cool thing we can do with policy is what I call binding. And this is a set of permissions that are from a node to another node. So there's no domains actually involved in these rules, but it allows us to define what the shape of XenStore should be. So in this case, these are the allow rules necessary to get us to the example that I showed at the start of this section here, where we say, first line, a node of type excess root T, the parent, is allowed to have children of type excess local domain T, the child. That's what this bind permission means. And so this gives us another degree of control that's basically orthogonal to the relationship between domains and nodes. It lets us say, you can only have these types of nodes in this place in XenStore. So that gives us a lot of control over not allowing domains to just create random nodes wherever. Like you can really lock down like where things can appear in the XenStore. All right. So even in this sort of small set of policy examples here, we're starting to notice some duplication in policy. And the SELinux policy language is pretty low-level language. So pretty quickly you find yourself wanting some form of abstraction. And what SELinux and XSM use are M4 macros. And so we do the same thing in our XenStore policy. And a great example of when those are really useful is when you have domains that provide device backends and then domains that have device front ends that have to connect those backends. So here we have an example of some much, much higher level policy that uses a bunch of macros. So in that first section there, we're defining the policy for DOM0. And so we say DOM0 is a domain, and that defines a lot of policy for the fact that DOM0 exists and is a domain. And then we can also say that DOM0 provides a virtual block device backend, and that creates another set of, it declares a bunch of types and creates allow rules for those. And then in the second section here, we create a DOM-U, same thing with access domain. Access control domain tells the policy that DOM0 is allowed to create and manage DOM0. So for example, it can unpause it, that sort of thing. In this case, a lot of that policy would actually be XSM policy, like the unpausing, but it basically kind of gives DOM0 super user powers over DOM-U's XenStore tree. Then finally, access device sets up this relationship between DOM-U and DOM0 that says DOM-U uses a virtual block device provided by DOM0. And this creates a whole slew of policy, which I am showing a small section of here, that's basically setting up all the rules about who can read and write what. And so in some cases, the front end has to be able to write to its own nodes. The front end and back end need to be able to read each other's nodes and so on. And we can see in blue here a bunch of labels that have been computed by sort of pasting together all those things. So the fact that it's a block device tells us how to label those nodes, and we know how to write, we know how to tie those two macros together by convention. All right. To summarize, mandatory access control is really cool. If you haven't checked out XSM, I highly recommend that you do. Play with it. You can do a lot with it. If you're going to use XSM, you should really be securing XenStore with MAC as well. And it just so happens that there is a lovely implementation of MAC for XenStore that can be installed via OPAM. And you'll get a nice Mirage kernel at the end of the build process. And so this is all open source, and our goal is to merge this into upstream Mirage. And I'd be happy to answer any questions you have. Yeah. So we do have an example policy that's included with the distribution, if that's sort of what you're thinking about. So it will already have default labeling rules for like all the sort of standard devices and DOM-Us and that sort of thing. Probably not. That would be an excellent opportunity for someone to contribute, I think. That's not a scenario that I tested, so I don't actually know, but my guess is it probably doesn't support that. I've mostly tested this with PV drivers. Uh-huh. Yeah, so we actually generate identical audit messages. So Xen actually does this for XSM. They look just like SELinux's audit messages, and so then we do the same thing as Xen as well. There is a little bit of trickiness with where they go, and this is another interesting place where there should be some future work, which is that, at least in our test system, XenStore starts so early that there's no console available. There's no Xen console available. So we were writing these messages to the hypervisor console, which is okay, but it would probably be nice for them to go to a sort of more typical console, go through the console ring and that sort of thing, because they're going to get lost if they go in the hypervisor output. Yeah. That would be a nice thing to do. We have not discussed that. Yeah. That would make a lot of sense to do. Yeah, absolutely. Uh-huh. Right. Right. Yeah, I mean, I definitely agree that that's a negative, but I think it's probably not that hard to come up with a system to get around that, because these sorts of policy statements are so high level that you could have another set of definitions for these that expand into the right XSM policy as well. So when you define, say, like access control domain, like I accidentally said it allows DOM0 to unpause DOMU, and that was incorrect. But you can imagine another definition of this, like maybe there's no XS underscore, it's just control domain. And maybe you have a build system that routes the policy this way through this set of macros for XSM and this way through a different set of macros for XenStore. And then they're coordinated together. And we had a prototype system where we did actually do the XenStore policy in the hypervisors policy, and that's how it worked, and it was very sort of straightforward. So I think you could do it pretty easily with some build system work. Any other questions? All right, thank you.